Our focus for today is going to be on composition of functions. Functions in themselves are just a series of operations on an input or some quantity that are working together to create an output. So for today's video, we're going to be focusing on two functions in particular, the function v and then the function z. V is a function in which our quantity x is being cubed, and then it's being doubled, and then 7 is being taken away. Z is another function, and it's being defined by the inverse of v. We represent the inverse of a function with a little -1 that's raised. So knowing that that little -1 means inverse, we have to recall our previous knowledge of what is an inverse. I know inverse operations, where like through addition, the inverse of addition are two numbers that are opposites of each other, so that when they're added, they create a 0. And then the inverse of multiplication is two numbers that are reciprocals of each other, that when being multiplied, they actually create 1. So if I take a function and its inverse, something needs to be created. And I have a feeling that it's going to be the identity, because 0 and 1 are the identities of addition and multiplication, respectively. So does that mean that functions have inverses and identities too? Well, the answer to that question is yes. If I take a function and its inverse and compose them within each other, I should be producing the identity. In mathematics, whatever situation that you're in, we use the inverse to obtain the identity. We obtain the identity by applying the inverse. So x is actually the identity function, or the function identity. And when I compose inverses within each other, inverse functions, when I compose them within each other, taking one input, getting an output, and then taking that output and then making it another input, I'm actually creating x pairs for each other, similarly to the 0 pairs and the 1 pairs of addition and multiplication. By composing inverse functions, we'll be creating x pairs, since the line y equals x is actually the identity function. X pairs are just like 0 pairs and 1 pairs. A number and its opposite, when added, make 0, the identity. A number and its reciprocal make 1 when they're being multiplied, which is the multiplicative identity. So focusing now on figuring out what our z function is, we need to analyze just what makes up our v function. Now, it's a series of little operations or little functions. v1, or the first operation that's being applied to my quantity in v, is a little function which is saying that x is being cubed or raised to the 3rd power. After that, v2, v sub 2 of x, of the quantity, is then taking that previous amount, that previous result, and multiplying it by 2. The third little operation in my v function is I'm taking that result after I've cubed it and after I doubled it, and I'm going to be decreasing it by 7. So to find out our z function, we need to know the inverse of all the parts that make up our function v. We know from previous knowledge that we want to create zeros and create ones because they are the identities of addition and multiplication. And we're going to extend that today by actually creating x pairs, because that is the function identity. So to create an x pair of my first operation is to take the inverse of a cubed number, which is a cube root. If I were to multiply them together, a cube number and then cube rooting it, it's the inverse. So they create an x pair. Another way to represent the cube root of a number is to have a rational exponent. So I'm going to be using x to the 1/3 power for the remainder of this video. For our second v sub 2 of x, the inverse of that is the reciprocal of 2. 2 times a quantity and then 1/2 times a quantity, they create an x pair. Similarly to the third part, v sub 3, the inverse of v sub 3 of x, instead of taking away 7, we're going to add 7. Knowing that z is the inverse of all of my v function, we're actually going to use all of the little inverse functions in an inverted order, because composition is not commutative. So I'm going to first start taking out that a quantity increased by 7. I'm going to take that entire quantity and multiply it by a half, 1/2 of that original number that is increased by 7. And then I'm going to cube root that entire quantity. So the build-up together of all of the inverses is my function z. So now that we worked to find z and we already have v, we need to check to see that v, the function v, and the function z truly are inverses of each other. We must prove that when they're composed within each other, they both produce the same result. And that result that we're looking for is the identity function, or x. So I want to take z of x and I want to compose it within v of x. Everywhere that there originally is an input, I'm going to take that quantity and I'm going to take it everywhere that there originally is an input quantity, I'm going to replace it with my entire function z. So I'm going to take my entire function z, I'm going to then cube it, then double it, and then take away 7. So you can see that that original quantity, that original input quantity x, was just replaced by my entire function z of x. So, taking a look at this step, I can see that a 1/3 power raised to a power of 3 in exponent laws simplifies to 1. So any quantity that's raised to the first power is itself. So I'm going to rewrite it. 2 times the entire quantity of 1/2 of x plus 7, take away 7. I see that 2 and 1/2 are reciprocals of each other. They create a 1. So they are one pair. That's the multiplication, the multiplicative identity. It's the do nothing. So I'm going to rewrite it with whatever I was left with. The quantity x plus 7, take away 7. By using the associative property, I can see that increasing by 7 and then taking away 7 actually create a 7 zero pairs, resulting in x, which is the identity function. So z of x composed within v of x actually created the identity function. But we're not done. We have to prove it on the other side. this time I'm going to take v of x and I'm going to compose it within z of x. Every time I see in my z function the input quantity, I'm going to replace it with the entire function v. So start without 2 times a quantity cubed times 2, take away 7, added to 7, taking that quantity, multiplying it by 1/2, and then taking that entire result and then finally raising it to a 1/3 power. Inside, I can see that, again, taking away 7 and then increasing by 7 creates 7 zero pairs, 0 being the additive identity. I'm left with this. 1/2 times a quantity, 2 times x cubed, all raised to the 1/3 power. Again, I see that 1/2 and 2 are a 1 pair. They're reciprocals of each other, creating the multiplicative identity, which again leaves me with a number cubed, all raised to the 1/3 power. A number cubed raised to 1/3 exponent, a power of a power, simplifies to 1. Any number raised to a single power is itself. So again, it leaves me with x, the identity function. So z of x composed within v of x, and then again on the other side, v of x composed within z of x, they're inverses of each other because they both produce the same result, the identity function, x. So looking at our original slide, we talked about this idea of taking inverse functions and composing them within each other because they were inverses of each other to create the identity. We use the inverse to obtain the identity, and that's exactly what we did. Instead of just thinking 0 pairs and 1 pairs are our only objectives, now we're going to add that we can create x pairs when we're talking about a series of operations that are happening or a function that's happening.